differences, then we can make cells very, very simple, even just binary units or spiking units, and assume that all the dynamics comes from the connectivity. But that's not actually true. The system has a lot of freedom to modulate the entities, the nodes, as well as the edges, and the complexity arises from the combination of all of that together. So,
yeah. That's interesting. And so there's a general theme emerging in life, life being a disequilibrium process and creating disequilibrium. A lot of the ideas about biosignatures come down to looking for some kind of disequilibrium in things like oxygen, free oxygen, which is hard to maintain in an atmosphere without something maintaining disequilibrium. Looking for disequilibrium chemistry is one of the sort of abstract ideas about biosignatures, but something that also impresses me about life, like enzymes, like the enzymes that are involved in respiration, is that they actually catalyze reactions and increase the speed of approach to equilibrium as well. And so in terms of thinking for biosignatures, I wonder what the thinking is about the competition between life as a way of catalyzing kinetic approach to equilibrium versus life as creating disequilibrium. And maybe I'll just start from the end. And
Right. So life as creating its own disequilibrium. Well, okay, so one of the things that I guess I was trying to really bring out in my talk had to do with the idea that we have, say, a very good understanding of non-equilibrium systems in physics. What we see as possibly one of the main differences between non-living and living systems is perhaps the self-actualization of some of these non-equilibrium properties. Now, this is kind of tricky to really fix on a mathematical level, because we could say that hurricanes are very good examples of systems that follow gradients, and by following gradients in a certain way, they actually create their own out of equilibrium states. So we have a bunch of non-equilibrium systems that basically do actually follow gradients and can be said to, sort of create conditions for their own existence. Now, having said that, it feels living systems have some, I don't know, perhaps more goal directedness to it. Now, I know that I mentioned some ideas of goal directedness already being embedded in physics, but there is something perhaps that is still missing, which is the self-actualization perhaps of goals. Because, well, one thing is to say, well, we have a particular, I don't know, variational principle, we write down this equation and we can predict the long-term behavior of a system. A different one is to say, well, what would be good for the system itself? So, and what would be good for the system itself kind of goes back to the point that, Netta raised of individuality. So we actually need to have that particular notion of individual as out of equilibrium. Many systems can be out of equilibrium, but only some of them are living. And why is that? And it feels like some of this, perhaps definition of individuality is the key that we are still missing to really characterize that. And once we have that, perhaps we will be able to say what it means for something to actually self-actualize, create its own conditions to stay out of equilibrium, to minimize entropy, and to do a bunch of, interesting things that living systems appear to be doing.
Yeah. So, Anna, you also mentioned entropy. Do you want to have any comments on this equilibrium versus disequilibrium? Or
Sure.
Yeah.
So, personally, I think that life or organisms crave equilibrium. Life wants to control its environment. The ideal environment would be something that I adapt to, and then I'm the best at, and nothing changes, and I'm great. Unfortunately, it's in this process of life maintaining itself, life trying to control the environment, life creates disequilibrium. So by existing, I'm making the environment less stable, and so I have to continue adapting. And if I don't do that, well, other life will do it, and then I will disappear. So I think the tension comes from the fact that while we wish everything was very stable, that we could control it, our existence prevents this stability from existing. And that's why we have to keep adapting and creating more disequilibrium.
Does anybody else have any comments you want to make on this topic?
I can add a couple of notes. So first of all, when you think about learning in nervous systems, then one way of, many, many theories of learning, but one way of thinking about it is that the system doesn't want to change. It likes to be static, and it likes to be least active as possible because it wants to be energetically efficient. But it will modify itself and perturb itself to respond to the expected input such that it doesn't have to respond. So you can think about synaptic plasticity as a mechanism of the system changing its insides such that the input is expected and it doesn't learn anything new. In other words, it's building that internal model of the world such that it can be left alone. So that's one notion. And the other notion is one of efficiency. So when we think about animal behavior or plant behavior or any organism's behavior, one of the things that's remarkable is how energetically efficient these systems are. And so they're trying to maintain that entropic, low organized state as efficiently as possible. And yet they're disrupting that because they need to act on the environment in order to obtain food, to obtain fuel, to learn from the environment, to avoid danger and all the rest of it. And so there's always that tension of how do I do what I need to do whilst being as efficient as possible.
That's very good. And anybody else want to make a comment on this?
Yeah, I'm 50-50 on this idea that organisms are efficient. Because I was reading recently that the Gila monster uses less than 1,000 calories a year. So that's less than you're using a day. And it's a fine organism. It's a large predatory animal. So, what's efficient for one organism is spectacularly inefficient for another. And coming back to disorder and catalysis and things, the catalysts aren't there to make chemistry happen fast. You can make chemistry happen fast really easily. Get a lump of sodium and drop it in your bath water and you'll see very fast chemistry happen. It's to make specific chemistry happen at a useful rate. And that's to arrange internal captured entropy, order, whatever you want to call it. And what happens outside, organisms actually don't care very much. So oxygen is actually it's a waste product, but actually it is at a thermodynamic disequilibrium. The oxygen should react with nitrogen in the atmosphere to form nitrate. So why doesn't life do that? Because it's just too difficult. It can't be bothered, So going from sort of internal order and catalysis to a biosignature is really hard because it depends so much on the organism involved.
That's actually, so we can move on to some other topics. I'd like to move on to another question. This is particularly for Bedwell. I think that it strikes me as that there's still a huge gap between the most complex molecules we can that we know how to synthesize abiotically or prebiotically, and the simplest enzyme that does something useful. Although my knowledge of enzymes is not comprehensive, but when I see these pictures of enzymes, Rubisco, whatever, they're more like nano machines. They're enormously complicated things, and I'm not aware of knowing the missing links in between, say, autocatalytic reactions or whatever, and enzymes. Is there any progress, or do you see any hope for progress in sort of figuring out what those intermediate steps were that led to really useful enzymes?
Yeah, we're working on it. But so here's the thing. There's nothing in biology that is not complex. So I think calling it a less complex or more complex is, to me, sort of doesn't make sense because everything is complex in biology. So there's no more complex enzyme, a simpler enzyme, especially when, as you also mentioned, we are not in a place of creating any of these molecules if we don't have that knowledge, right? So when it comes to having the opportunity or the ability to generate any of these molecules, it's not going to be as simple, let's create or think about how we can transition from a simple molecule or a complex organic molecule or inorganic, whatever, to an enzyme. We will have to think about, we will have to come up with strategies similar to what a cell does, if I may. right? So this is not a new concept. Like about 40 years ago, Ganti was, I think, the one to propose the chemoton, right? Like since then, I think we're able to abstract and life into three main components that it's able to. There's information, there's informatics in biology, there's metabolism, and there's compartments. So all these three components are almost like a three legs to a bar stool. You remove one, the whole thing falls apart. So if you wanna create an enzyme, you need to fill these three components and think collectively. Autocatalysis I think there's autocatalysis to some degree in information as well, in the way life does. So if you can apply those to how life is able to compute, even though I'm not a fan of that term when it comes to biology, but let's use it for the sake, lack of a better word for now. There's an informatic process, there's a metabolic process, and as long as they're encapsulated, only then you will be able to create molecules. I don't think it's going to be as simple as, let me just see one day I'm going to evolve a simple enzyme.
Yeah, but well, we need a code also, because at the very center of what we call life, there is a code, of course. Yes, so I mean, there is this question where the chemistry ends and biology begins, and that's probably, is because we have coded information. So we have to have this. If we solve that problem, how the code developed, then we probably will be able to actually look more comprehensively at the problem of origin of life. Because currently, we could look at our genetic code and think that it is a little bit arbitrary. It could be different technically. Of course, we can come up with various hypotheses why it is the way it is, but we have to come up with a reasonable hypothesis why life would actually choose this type of code of translating information from one polymeric molecule into another. That is not necessarily purely chemical in nature. It's actually a coded information transfer. So that's, I think, at the center of what life is, and also how life originated. Once we figure this out, then we will be in a much better shape, I guess.
I completely agree with this. And if I may add, we can argue about what life is or what it does and appropriate evolution, which I think nothing is more appropriated than evolution and misunderstood than evolution than any other thing in biology. All right. There's no tendency for complexity in evolution. Like there's a lot of examples where actual natural selection works against increasing complexity. So let's retire that language forever. Here and not.
But there is some minimal complexity that life would need. That's the thing.
We can talk about that. But what we will, I think, need as a community is to come up with some sort of, we need to do the experiments, right? We're not going to be able to reduce life to a simple metric. That's not going to happen. But the nice thing about experiments and chemical experiments, biological experiments, is that they're much cheaper than building a telescope. All right, they're much more affordable, and I think models are great. This is a great start, and I think it really helps us provide that concept. But I don't know why we are not more data driven when it comes to talking and thinking about alternatives to life, and that's also a call for biology or biochemists who may be listening to this. That it's time that we think about how we can actually experimentally test and generate data instead of just arguing about ideas, because that's not going to get us far.
Yeah. And actually, this bridges another thing I was related to another thing I was wondering about, that things like the game of life and the complex patterns it can exhibit, and also the newer approaches to a life, which show how complexity evolves. They're digital, and even though there's progress in sort of minimal design of the rules, there's still something that's happening in silicon. And I'm wondering, is there any ability to, say, implement the game of life through chemical networks or something like it, actually, to give an indication of how these things could happen out in the real world as opposed to the digital world?
Do you want to go or? Okay. So one big issue with the game of life is that it's very fragile. You change one pixel and then everything collapses. One property of life is that it's very robust. It doesn't depend on just one thing, and you remove this one thing and now the organism has disappeared. So implementing the game of life itself in chemistry, I think, would be very difficult, if not impossible. But some of the newer approaches, like Lenya, Manuel talked a bit about it, they show more promise. There is a team that implemented a Gray-Scott model where you have this, it's not protocell, but like droplets that divide and that can learn how to avoid poisoning. And they are implementing it in real chemistry, for example. So there are some paths from some models to some chemistry. But I wonder if that's really the way to go, because I find it much more interesting to start from the real life and then see what kind of abstraction I can form from this real life than trying to build artificial life, which may rely on completely impossible physics or impossible chemistry, and then try to basically like force it to obey to the rules of this world.
Yeah, any other remarks on that?
I very much agree with this point of view. Like, part of so there would be clearly like technical challenges, like, to translate some of the physics of this game of life. Like, there are the physics of, of the game of life are very different from the physics, say, that we experience, say, in our physical world. And I would very much not want to try and bring it back, to like the value that I see in this kind of systems is probably due to how exotic and different they look like from, physics that we see in the real world. In our, say, real world, I am puzzled by the idea of, focusing on a single phylogenetic tree, as the only, as the only possible way to understand, something as complex as life. When somebody gives me a point and that asks me, well, what kind of function goes through that point? Well, there are infinite functions that can go through a single point. The idea to have different implementations, different possible universes to explore, I think is powerful because they are different, and because we shouldn't necessarily try to bring them, to exist on the same, set of physical laws.
Yeah, but to be fair to your point, that if we're going to look at real life and then try to abstract from it, we only have one phylogenetic tree to look at. So we can't say, let's invent another one and then grow it and evolve it for 3.5 billion years and then look at that, because the grant will run out.
I think
No, we should do that. That's the whole point.
So I think back to Manuel's point, one of the values of building artificial life systems is that they challenge our definition of life. And I think the value in that is that when we consider some other planets with exotic physics, and we think, well, life could not possibly exist there because of this and this constraint. If I can point to an artificial life system that doesn't have this constraint, then I can say, well, actually, these constraints are only constraints for life on Earth and not life on, world that we don't know.
Yeah. So soon we're going to move on to the audience questions. I had one more question to throw out, especially for Janos. Our field is very data driven, and we need more and more data, both from observations and from lab experiments. So I'm very fascinated by what the Venus mission is going to look for, what instruments it's going to have, and what it will be able to look for. So do you have any comments on that?
Yes, of course. Thank you very much. So the Morningstar missions, the Venus initiative, essentially has a series of concept missions in development, but the first mission in the series is the Rocket Lab mission to Venus, as it is called. And it has a very wonderful, unique instrument, an so-called autofluorescence nephelometer on board. And this is a wonderful work of Dr. Darren Baumgartner, who developed this instrument with his team. And what it will do is actually it will characterize the physical and chemical properties of the clouds. So it will be able to actually characterize the shape, the sizes of particles, and also, very importantly, this is where the so-called autofluorescence part comes in, is it will look at the fluorescence of these individual particles as well. And why we are looking at that specifically is because once we detect the fluorescence, we will excite this different material in the droplets, in the individual droplets, and once we actually detect the fluorescence from them, we will be able to use that as a proxy for hopefully organic chemistry, because the Rocket Lab mission to Venus actually is the first mission to ever ask the question whether organic chemistry in the clouds of Venus is there, and we are capable of doing that. And basically what we will be able to do, hopefully, is to detect and confirm that indeed the organic chemistry is there through the fluorescence. We will not know what organic chemicals we detect. That's the next missions in the series. Hopefully we will be able then to identify these molecules. But the first Rocket Lab mission is just going to give us a sort of a yes or no simple answer on that question. But that's a stuff, and it's a very important one, because until 3-4 years ago, nobody even believed that organic chemistry in concentrated sulfuric acid is possible. Now we know that not only this environment is not hostile to organic chemistry, it's actually conducive to it, and it results in the formation of many different, quite unique chemical systems. So yes, let's cross our fingers for the success of these developments, and we will see. So.
Well, that's excellent. And go ahead. Can I just add to that? I mean, people don't understand how little we know about Venus. So the clouds were last examined in any detail by the Pioneer Venus mission in 1982, something like that.
85.
85.
This was the Vega balloon. Yes.
And they did some basic sizing on the cloud particles, and they can't decide whether the larger particles are round or not. If they're not round, they're not droplets. If they're round, they could be droplets. So this is the level of we don't genuinely know what the clouds are made of. And so even this small and apparently simple instrument is going to really take our knowledge forward. It's really exciting.
Absolutely. Yeah, and I've learned from Cambridge thesis vibe I was involved in with Paul Rimmer's group that we don't really even understand the full sulfur chemistry in the clouds of Venus yet. There's big mysteries on just the basic inorganic sulfur chemistry.
Yeah, there's loads of stuff that said, well, we can model this. How do you do that? Well, we just set that to 0 because we think it is. Yes.
And we've acquired 50 years of observations. And there are some, I call them anomalies in the clouds. Yes? And there are many different instances when we detected various different, or allegedly detected various different gases of the 50 years of observations of Venus. And we are still arguing decades after these detections were made, whether these gases are there. For example, there is a question of oxygen in the clouds of Venus. There is a question of ammonia that is recurring from time to time. And there is, of course, almost 100-year-old question of the so-called unknown absorber in the clouds of Venus, a year from now, we are going to have around 100-year anniversary of the detection of the absorber, and we are still, 100 years later, we are arguing what this absorber is. And those are these sort of black streaks of something in the clouds of Venus that we do not know what they are. And so, yes, hopefully we will be able to shed some light on this.
Yeah, and I think you had a...
Oh yeah, sorry, very self-interested question, but will you have any time series for me to get excited about?
Sorry, what?
Time series.
Time series on the reactivity of these or changes of anything,
yes,
any time.
Any time series.
There's lots of time series on the UV absorber from remote.
Yes.
I think the Rocket Labs mission is going to fall through the clouds in about 5 minutes.
Yes, if I'm
rather short time series.
This is enough to collect the data. And analyze everything. But yes, like for example, we have long-term observations, not we as a humanity, have long-term observations of the absorber. And we, for example, know that this is a dynamic phenomenon. That's actually, that you might be interested in that, because it is a dynamic phenomenon that changes in space and time. It follows a quasi-seasonal changes. Of course, Venus as itself doesn't have seasons per se, but it sort of has these sort of changes, which, who knows, maybe follow the sun activity, or so I don't have no idea. But so yes, this is definitely there are some time series data that potentially you could use. Yes.
Thank you.
Yeah.
Okay, I think it's time to move on to audience questions now. If we have time, we can go back. So I think Paul Rimmer, Paul, you have here. So I don't have I guess someone will get you a microphone or toss you a foam cube. Paul.
I just wanted to bring up this really interesting point about finding artificial life and using that as an example of what life is capable of. I think that there's a certain sense in which that's true. We might be able to build life, but then if you found something like that, would that tell you that that some technologically capable civilization has built this life, or that this life arose naturally. And I guess the sort of broader question is, how important is trying to figure out ways in which these molecules could arise naturally? How important is that for answering the questions of whether there could be life in these different environments? Is that important at all at the first stage, or how does that part of it fit in?
Are you asking by naturally, do you mean abiotically, or?
Yeah, like, I mean, without like already being there to build it, like, you might be able to create Venturous cell, but if you knew enough, you'd probably say, oh, someone spent a lot of time and money building that. Versus if you happen to find Luca, you would say something, you might say that, well, this could have just arisen on its own without some other life being there that either reproduced it or that built it.
Yeah, I mean, finding evidence for life may even be easier than finding evidence for absence of life, right? I mean, that's equally important for sure. When I teach this when I teach astrobiology class, like I tell the students, what's the first question you ask when anyone claims there's some certain, eureka, whatever biosignature molecule, and that is that. In what ways can this planet fool me? What are the abiotic pathways in which this can occur? And not knowing those pathways doesn't mean that it cannot happen abiotically. So absolutely necessary, I think, to invest in creating some sort of library of for our own understanding of chemical reactions, not just sets of reactions, but networks as well, to understand that abiotic pathways. I think it would be great to have our own sort of library of Alexandra, so to speak, of abiotic reactions. That would be a great source.
Yes, go ahead.
I think your question relates to the question by Sarah Walker, which is you go on the moon and you find a watch. Do you assume that the watch, just emerged from the moon, or somebody built the watch and put it there? And I don't think there are a lot of ways to answer this question, except by looking for code. So the watch, there is no code in the watch that codes for the watch. So it didn't evolve. It was created by, me or somebody. But if you can find a code and you can find several instances of this watch or whatever it is, then you can compare it and say, okay, there was some evolution happening, and we can trace it back to Luca or something. And therefore, we can try to infer whether this life was evolved on this planet or on a different planet.
I mean, I could maybe question that. Should I get
Netta.
on the first? So to push back on that, so if you look at the von Neumann machine, that had the code inside. Everything was inside, and it replicated itself. And if you think about sort of AI, and if AI becomes sufficiently intelligent, you could think of AI is disembodied in a sense. It's running on Turing machines, right? So on universal computers on the cloud. And so you can imagine an AI that's smart enough to design a life form and then get robots to build that thing that then will include the code and develops into life. But again, there was initially some creator.
I don't think we disagree. I think we agree because, say, the von Neumann machine, there is a code and it can self-replicate. If you have several examples of the von Neumann machine, you can go back to the original code before there was any kind of evolution.
If you have it, yeah. Mm-hmm. If you have enough of it.
Okay, I'd like to take another question. Yes, back there.
Hello, David Garn. I've got a two-part question. One about hydrology or its equivalent on Venus. Any ideas about that? And also about cyclical environments as forcing functions for evolution or even for cellular automata. I'm quite a fan of David Diemer and his co-workers' ideas about the little volcanic island where it rains and whatever's there is subject to sequential desiccation and hydration, which provides kind of two different environments for the prebiotic molecules in the two different, effectively, forcing functions. So do we have any ideas of the clouds of Venus? Is there any kind of transport mechanisms that anyone has guessed at, the equivalent of the hydrological cycle? And also generalizing that to the other panel members, do we spend too much time thinking about the system itself and not about the oscillating environment as a forcing function?
You take clouds, I'll take Dima.
Yes. is a deal. Yes, so we can essentially boil down the question, do we actually... Okay, you essentially ask a question about the origin of life scenarios in the Venusian clouds. Well, we cannot answer this question for more than, now more, I guess, 100 years, since Oparin formulated this problem, 100 years ago again. But technically, we can imagine some sort of cycling and dynamic behavior in the clouds of Venus that could actually give rise to some sort of selection processes of these molecules in the clouds. Why? Because the droplets travel through the cloud deck, yes, and as they travel through the cloud deck, they change the temperature conditions, for example, or even probably the acidity of the acid of the droplets. We shouldn't expect that at each level of the clouds, the acidity of the droplet is the same. So you have at least two factors that are going to be meaningfully changed potentially. It's the acidity of the individual droplets and also the temperature. How that affects the changes of the chemistry and organic chemistry in the clouds, and would that lead to a rise of some sort of code, yes, which we would really need to distinguish chemistry from biology. And I cannot even speculate because we are not at this level yet. We tried to solve the origin of life in water for 100 years, and we are not there yet. We started our sulfuric acid avenues 4 years ago. So we have a lot of work ahead of us.
Yeah. So I'd like to give most possible people opportunity. So if we have questions over here. Yeah.
I think you didn't talk about dimmer, and I was waiting for that, but you will get back to it. One question, do you think it matters whether life originated spontaneously or is it product of seeded life? Because I don't see a problem if it's one or either. We should study it either way. And to what Janusz was talking about, I see the biggest problem for life in clouds of Venus in how you seed next droplets, because droplets emerge together and then they fall from the cloud. I can't imagine mechanism how you spread from that one droplet and seed other droplets. So
Absolutely. It's because the droplets do not fragment. That we know. But the fact that we cannot... sorry.
Question for the panel would be about the, why should we care if the life is artificial or, natural?
Yeah. So we got a couple of potential mechanisms how life could spread between droplets, which I can talk to you about or somebody about afterwards. I think on the origin of life, David Deemer's idea is that life originated in surface volcanic pools, so you get them drying out and re-wetting, and you get cycles of dehydration, hydration, lamellar membrane formation. It all sounds great. I think it's all made up. I think we know nothing at all about the origin of life. We literally know nothing. We know quite a lot about the organic chemistry that might happen in the conditions that might have been present in some places on early Earth. And we have some idea of what Luca, this last universal common ancestor, looked like. And there's a vast gap in between, which, as Janusz said, in my view, we've made no progress in the last 100 years. So, sorry, guys.
Yep. Here's a question over there. Yep.
My question's about what it would mean to us as a society, as a civilization, if tomorrow there was an announcement of definitive, unambiguous evidence of extraterrestrial life. I've been really blown away by the immense work that you've shared with us that's going on right now. And I was always under the impression that finding life, primitive life, is fairly inevitable in the next decade or so, and perhaps after today, I think it's going to be even sooner. I'm old enough to remember when black holes and extrasolar planets were really not quite certain about. Today, we know about thousands of exoplanets. Black holes are very familiar objects. So my question is, if there was some evidence, and I think it's, from what I've heard, it's pretty much inevitable in the next few years, certainly before the end of this decade, it's my feeling. What are the consequences? Will it be a big deal for us? Is it the kind of holy grail question that we've been looking for? Is it going to be a big deal for us?
Yeah, good. Yep.
So I think if we have such an announcement and people are convinced by the announcement, I think it will be a crisis for a lot of humanity. You talked about the Holy Grail. If you are a religious person, it might be a crisis for you to find that there is life on other planets and that this life has nothing to do with us, with humans. But even beyond that, even if you're not a very spiritual person, a lot of people assume that humans are very, very special, that Earth is very special and important. And we would suddenly find that we are not that special or that important. And hopefully that would bring some interesting changes into society.
Wouldn't that be nice? I completely disagree.
Okay.
I think it would make no difference whatsoever, apart from a change of the news cycle for about 48 hours. I think the late Pope Francis has already stated that finding life on other worlds would not contradict Catholic faith, because if God can create life on this world, he can create it on others. Most people think their own village or town is more special than the rest of the world, and they know the rest of the world is there. I would love to think it would open a new era of more openness and generosity in humanity, and I don't think it will.
I can agree and disagree with you both, maybe.
Excellent.
So we already mentioned that life is risk averse. Life is also selfish and centric. So humans are very human centric. And so that in that sense, I agree with you. But religion teaches us humility. But 300 years after Darwin, half of humanity doesn't accept Darwin. And so, we do everything so long as it helps us with our imagined self-preservation, which may or may not actually help our self-preservation. And so it's going to be complicated.
So can I bring something else? Maybe not a lot of people. Some people recently are very worried about what they call existential risk from AI. Oh, AI is going to kill us. What are we going to do? I think if we found evidence of life elsewhere, people would be more worried about that. And I do think people would care.
Well, don't forget about 20% of people believe that we found lots of evidence elsewhere, and it's flying around the Earth in flying saucers at the moment.
20% of US people, no?
Well, Americans, yes, so not people, but...
No, I mean, it's not 20% of the whole Earth.
I saw a paper a little while ago, 10% of the population of the UK, 9% of the population of Sweden believe in witches, in witchcraft. So...
the rest believe that rocks are alive.
Yes, or whatever. So we're extraordinarily atypical audience here.
But will it make a difference, what kind of life could be found? What I mean, if we found life as we know it elsewhere, I think the news would be probably less groundbreaking than, finding some really exotic new life form that really took a long time, even just to make sure that it was actually a living system. I don't know, it feels like the reactions could be very different, from a social perspective, from a religious perspective, from a scientific perspective.
From us, yeah.
I don't think it would make a real difference if we discovered life and it was on a relativistic starship heading towards Earth. And then we'd say, oh dear.
I think it's a too pessimistic view of humanity, People like science. People really like this, little scientific...
They like David Attenborough documentaries. They don't like science.
Yeah, I think it's very difficult. It's very difficult to predict how humanity is going to respond to new discoveries. There's actually been, I don't think anybody could have really predicted how humanity is responding to the growth of AI. I mean, I think a lot of the artificial general intelligence is overhyped right now. We're not really anywhere close to that, or the risk of it taking us over. I'm much more worried about carbon dioxide and climate as an existential risk myself. But until we actually discover some form of life, it's going to be really hard. But something that concerns me is that if we have a lot of premature announcements of discovery of life, as we've had recently, people will just get exhausted. They'll think life has been discovered, and when it finally comes out, that a real discovery, people will be exhausted by all the false discoveries. But
There's a great science fiction novel there, actually, isn't there, where that's done deliberately to inoculate the population. So when we do finally discover aliens, they say, "Oh, that's fine."
yeah.
No, this will be a gradual process. I mean, I think that we, in the era of JWST and all the space missions that are being developed in our own solar system, we will probably simply discover life by gathering the evidence. Yes, and eventually, hopefully, we are going to have maybe enough data to make some sort of meaningful statistical predictions about, for example, its prevalence in the cosmos. So I don't really think, short of the Williams and others flying saucer scenarios, when this is a sort of a 0-1 type of a situation, we are probably going to inch our way towards an actual discovery of true extraterrestrial life. It's not going to be the one night we are waking up, one day, sorry, or maybe night, we are waking up and we are in the cosmos that is actually suddenly less lonely.
I want to also add something that I think it goes back to what degree are we able to embrace and appreciate life on this planet, right? We discover weird life forms on the bottom of the ocean every day. We know hardly anything really about the current diversity of life. And to what degree are we able to excite public with this knowledge? And by that, I really mean children and students, right? As long as we keep that fire going, I think the future is fine. I find this language about public being anti-science or not understanding, not getting it, very problematic. I think we need to retire from that language. I think it didn't serve our community well. We are not removed from society, right? We, like, as scientists, we are very much grateful to them. We are, when we need them to support it. And most importantly, basic science has to be supported. I see these things hand in hand. Search for life in the universe, understanding life here, infusing society and especially young generation with the awe of science, that they are together. So it's not going to do anything different than what real science and basic science is already doing to this planet. And that's what we need to protect.
So we only have about 3 minutes left. So there'll be time for more discussions over lunch and breaks and so forth. I'd like to thank the panel for all this really fascinating. I wish we could go on all afternoon. There's a lot to talk about here, but let's do the quiz.
Let's do the quiz, you guys. Hey, but pick it out.
I think so far the answer's 42.
So let's do it.
What's going on?
We should look for patterns. What's the F-zero machine?
Times.
Oh, we have a cluster.
I mean, if you don't know the answer to this, please leave. You leave.
Actually, it's kind of tricky.
How are you meant to participate in this?
I think they do.
No, it's an audio.
How are they meant to participate? There's a QR some sort of tab.
You will know answers to it.
Kahoot is the app, and they will give a QR code for the specific survey.
So this is some modern technological thing. You young people use it.
Exactly what you have to do if you go to conferences these days. Yeah. 41 answers.
Tolkien should be able to answer.
Very nice. Our conflict between him. The question is, it all depends on our morals, and we can't predict what the morals of a new generation will be, but we can predict that morality keeps cycling over humanity. It keeps cycling between being reinforcing morality again and again and again. But I think aliens would doubt it. It's gonna be cool. I don't understand the pessimism because I don't find it hard to, because at the moment we're pessimist. No, I don't find it hard to get excited about that. Inevitably to be excited about that. Yes, but some of that excitement is very misguided. What you see.
Really? Oh, okay. So we actually have quite a lot of Trekkies in the audience. Yes, and my favorite scene is where Spock does the Vulcan mind meld with the Horde. But
I trust you're going to try it for a second.
yeah,
It's
live long and prosper.
It's episode 26 called "The Devil in the Dark" from season 1.
Wow. What am I doing on this part?
There you go.
Yeah. But it must have had some amazing kind of metabolism to keep its internal heat hot enough for silicon-based reactions in a situation where Captain Kirk could just walk around in his shirt sleeves and not fry.
We could talk around the chemistry of silicon-based life later.
Yeah, I guess it's time we can go on to the next one.
Is there a right answer to this question? I disagree with the existence of this question.
Well, it can't be yellow because then it will be civilization that split it.
Might be all dramatic. I could argue there's no difference between red and blue here.
Why?
Because self-replicating AI is a form of synthetic life.
Is it?
I mean, in this context, I don't know what it is, so it could.
Yeah, that's right. I mean, we are for silicon-based life. AI is silicon-based life, and it has we have been brought into existence as an intermediary to create that form of silicon-based life.
Yes, we need to define life. We need to define system. We need to define individual in order to, you need to say whether it has the code inside it or not. And so
This should be option D. This is not a world formula. Correct question.
indeed.
Is that how?
Yeah, we vote.
Yeah, and actually, the blue and identify habitable worlds and send synthetic life to jumpstart evolution. I mean, I think that's actually something that we'll have the capability of eventually in the next couple centuries. And it takes a long time for living things to cross the galaxy, but
We don't need to just think of synthetic life, but we could also think about studying the planet, identifying the missing chemicals that will push whatever life form to its whole flourishment, and then send those missing chemicals to the planet.
Yeah. So, for example, it took 2.5 billion years for oxygenic photosynthesis on Earth. Maybe we could jumpstart that. But should we? There's ethical questions.
Option A is rather problematic because it says let AI discover life, but then still wait for the speed for slow transport. But if we have AI and we have radio communication, then it may be that life can be sprouted remotely without actually having to go there.
None of the answers are.
Well, where is the AI? AI will do it.
You're all more to skip. Everything is
It's like
Then you can also question.
always bet on it.
we will let data speak.
If she wants funding.
Or is
After
it
our
everything
opinion.
else being equal?
No AI, no life.
There is no AI without AI.
Is that the yellow one is kind of catching your question?
Wow.
Yeah.
Panspermia.
People would say that because it is, isn't it?
Yeah, actually, the question about whether it would be too dangerous already came up. That's come up with the idea of opposite chirality lights. Whether this would, because it probably, I don't know how close we are to being able to make opposite chirality life, but different handedness. But it does seem like something that could be dangerous if it got loose. But there's been a lot of discussion of that. But
Well, I would start from first creating life as we know it, just recreating our own life from scratch, not just by emptying the cell and putting everything back together. Yeah.
Yes, yeah. Well, I think that's it. And so now it's time for lunch, or in fact a little bit over time. And so we have much more to come in the afternoon and tomorrow. So thanks again to everybody who's participated this morning.
Thank you.